Recently, IB and NASA teamed up to create a foundational Earth observation model called Prithvi that can do several different operations. It can detect things like burn scars using Earth observation data, crop classification, and a few other operations. And what's really unique about this is that you don't have to do any model training yourself. Basically, NASA and IBM teamed up to use their computing power and satellite resources to create this foundational model. That means it trains on a lot of data, so it's seen a lot of different things, and you can use it effectively just by yourself without any training data. The only tricky part is you have to get the data in the right format. So in this tutorial, we're going to take a look at this specific foundational model, talk a little bit about what foundational models are and why you should care about them, actually download some data and crunch it together in QGIS so you can actually use the user interface for this model, which is hosted on Hugging Face, and then predict some cropland classification from that. So with that, let's go ahead and get started. So, if you have never done any machine learning, deep learning, image classification, anything like that, I'll certainly tell you one of the hardest parts about doing that is getting enough training data to create a functional model. On the simplest level, if you think about machine learning as some sort of in the simplest of simple terms, if you think about machine learning, you're taking some sort of data and something maybe that's happened in the past or some observation to predict what may happen in the future. Now, there's a few different, that's a very simplified explanation, but effectively that's what you're trying to do. There's a few different methods of that. You might be actually trying to predict a value. Basically, is this going to be a 1, a 0, a 5,000, whatever that is, some numerical value? That could be a classification. Does it fall in class A, B, C, or D? Or is it, basically true or false, right? You could be, doing one or the other. And there's different levels to that, of course, as well. But just as the simplest possible explainer, that's like a very easy way to look at that. And the easiest way to think about this is just some simple, linear regression charts. This one's a little bit more advanced, but I think, just for visualization purposes, this will help. So if you see all these dots, you can kind of figure out that there is a trend here of, as X increases, so will Y at a certain rate, right? It will go up. Now, if you only have a few dots, you can still make a prediction, but it's going to be a lot less accurate to predict the next dot coming in. But the more dots you have, the more accurate your prediction can become. And that's a very simple linear regression model. This is what that's known as. And it's just saying, two variables, figuring out between those two variables, what does that look like? A really common example that I hear is, trying to figure out, okay, based on the number of bedrooms a house has, can I predict the sale price? Or the number of square feet, can I predict the sale price? And that's a very simplified example, but it's one that can make sense from there. Now, as it relates to Earth observation, you're using, instead of points, you're using pixels or the different, bands from the satellite image that's coming through, the R, the G, the B, red, green, and blue. And then, with the Sentinel-2 data, or you're using many other bands of data that are being pulled from that data. And that allows you to make different predictions or classifications or anything like that. The specific example, like I said, we'll be looking at with the IBM NASA Prithvi models are land or crop classification, crop type classification. Now, there's different foundational models. There's an example here. This is the clay foundational model, and there's some good tutorials you can kind of check out to see what those do. Some other ones I've seen here is this sort of Earth PT. It's another type of foundational model that's basically trying to create a model off of lots and lots of data. So by adding way more data over a much larger period of time, the idea is that the model will become really, really good and useful so that you can take it without having to, first of all, collect all that data yourselves. We're talking massive amounts of imagery that are collected over long periods of time. That's number one. And number two, just having the computing resources to actually do the training of that model is a whole other thing. It takes a lot of power, machine power. And if you were doing this on your own, you might have access to your local laptop, and sometimes you can do that. But most times, specifically with the images and the detail of these images, you need some sort of extra computing resource. And oftentimes it's a GPU computing resource, which is not cheap. Those cost quite a bit when you're looking at a cloud provider. So that's the huge advantage is number one, you don't actually have to be in charge of getting any of that data. You can use the model as is. The second piece is that you definitely don't have to onboard the computing cost for that model, right? Now, of course, there's downsides. You may or may not have as much control over that model, and you may or may not know some of the weights or like when I say weights, the feature weights that go into ad. You can't adjust that should you choose to do so. So you lose some control, but you're kind of trading off the balance of not having to pay for computing or data storage for basically getting access to this model and being able to do that. So this is just a quick example of what one of these models would look like. I'll put these links in the description here so you can take a look at these from EarthBT and the Clay foundational models as well. So this is basically where these models, these Prithvi models are hosted. This is a tool called Hugging Face. And you may or may not have heard of this, but it's becoming increasingly popular, especially with the growth of the large language models. And Hugging Face is a place where many people are hosting these models, as well as some of the data sets that are being used to train these models. So you can actually use and go here and search for different LLMs, large language models that are being used. It also gives you code to actually implement them. But of course, that's a topic for another day. We're here to look at the Prithvi model here. And you can go through and take a look at some of the information here. But basically, you can see here that they've teamed up, IBM and NASA have teamed up to create the AI foundational model for Earth observation, right? And as it says, it uses the imagery, it uses the harmonized Landsat and Sentinel-2 data. And since it's embracing these principles of open AI and open science, they want to contribute back to that mission. So great. So with the Hugging Face platform, which we're on here, it can simplify the geospatial model training and development and make it open for access and users. And then should you choose, you can, if you want to use the multi-cloud AI platforms, deploy this, their software, you certainly can do that. So this is the Prithvi model. If you are so inclined, you can get into the technical paper here and read a little bit about that. If that's sort of your cup of tea, go ahead. And then you can also check out some of the information here, some of the fine-tuned versions of these models and things like that. So there's the models for downscaling, and this is biomass. I haven't actually checked these ones out yet, but these are other ones you could certainly take a look at and see. So getting back to here, you can see as you go down here, there's 4 what are called spaces. There's 4 models. So there's these sentinel floods, the classification, which is what we'll be using, the burn scars, and then the full 100-meter demo, right? So this is looking at, let's see, it's a transformer, self-supervised encoder. Yeah, I don't actually know what this one is. I haven't checked this one out yet. So what you can see here is let's click in the one we're going to be doing today, which is the multi-temporal crop classification model. So it's a little bit of a mouthful, but as you can see, multi-temporal or taking snapshots over time of crop classification for the U.S. harmonized Landsat Sentinel-2 data. And what you can see here is it's asking you to drop a file. And we'll get to the specifics of how to build that file in a minute because it's a little bit tricky. But you have some examples down here. Here's the legend of what it will predict. So if I can open that in a new tab, you can see here that these are the colors that it will classify. They'll have natural vegetation, forest, corn, soybeans, wetlands, developed or barren, water or open water, wheat, alfalfa, sorghum, cotton, fallow, idle cropland, or other. So it's a classification model, meaning that it wants to classify each pixel into one of these different types of things. So you can see here there's a few examples, right? So let's just click this one in the middle and it will load it up, and you can see here that these are different images over time, right? And it'll basically, you can see each of these. Now this is preloaded, so if we open this up in a new tab, you can see here that this is what it's returned. Basically, here's some different areas and what it returns. And you can actually submit this and it will run the model for you. You can see the processing time. This one should run a little bit faster. It's telling me it's going to take 2,400 seconds, which seems like quite a bit. So we'll see if that's actually the case. But that's actually running the model. These examples usually run a little bit quicker, but we'll see why that is today. So that's what's running now. It's going to, take some time to do that on a specific period. But what I want to look at, and maybe I'll just refresh this for now, is what data we need to get and how we need to structure it. So that's this piece here. So in this sentence, the user needs to provide an HLS geotiff image, including 18 bands, for a 3 time step. So what that means is that you'll have 18 total bands, but over 3 times. So there'll be a chunk of 3 from date period 1, chunk of 3 from date period 2, and chunk of 3 from date period 3. So that's your job to do to make this whole thing work. And then it needs to have these channels from the HLS data, which is blue, green, red, narrow, and near infrared, and then SW infrared. I don't forget what SW means. And SW, I think shortwave. I don't know. I can't remember. So SWIR2 in that order. So first job is to find and figure out where to get our HLS Sentinel-2 data. Let's take a look at this area. We can look here in Minnesota, maybe Iowa, and kind of see that there's a lot of farmland here, obviously. So you can see here, these are obviously farms, and then this is obviously, you know, river and forest and water. So we have some diversity here, and we can kind of figure out where this area is. So that's what we're going to do. Now, to get that data, we need to go to and actually find this data. So if you go to search.earthdata.nasa.gov, you can actually go to this portal, and then you'll actually be able to open it up and find these different data sets that you want. So to do that, we'll just take a quick step back here, because that's the search that I cached before. When you first land on this, you'll want to go to like your area of interest. So if you remember, we were looking in southern Minnesota here. I don't know if there's a specific like geo search feature here that I can actually just type in the location. But let's just kind of roughly figure out where we are in reference to what we can see on the map. So here is this area we were looking at, straight south of Mankato. So that was referenced here. You can see straight south of Mankato, and we can just draw a very simple bounding box here. It doesn't have to be massive, so we'll just call it that. So first step, just give it the area of interest that you want. It's going to go through and look through all the data sets or the collections that it has available, but we want that HLS data. So let's go HLS, and we'll hit enter here, and then that will look for the data that we need. So you'll see there's a few options here. HLS Landsat operational. Well, the one that we want is the Sentinel-2 multispectral instrument surface reflection daily global 30 meter V2. That's the one that we want to look for. So let's go back here, and we want the, I'm already forgetting all what I just rattled off there. So it's the HLS multispectral surface reflexant. All right, and that is this data set here. So let's go ahead and click that, and it should filter to our spatial area here. And you can see on the bottom here when this was running. So, you know, you can get images over these different periods of time, and then you'll start to see, you know, a quick preview of those here. Now, what we want to do is kind of get some samples during the growing season, you know, so we're looking at this summer period, July, September, somewhere in there. We could even go into October if we really wanted to. But let's find images that are of high quality, 1, and then 2, images that I'm sorry, when I say high quality, limited cloud cover, and then a sample over 3 chunks of time. So that's what we're going to do. So the first thing that we want to do is get some images and actually download them from the Earth Data Search. So we have the right data collection, and now we just need to pick some dates. And generally you want to, you know, since we're looking at crops, let's pick a few different dates for the growing period. So we can kind of look through this, you know, October, September, August, July, and that's just happens to be the time frame that we're in right now. And I found this image here. So this image here is from September 20th of 2024, and it looks, you know, fairly clean. When I actually select it here, you get a little preview of that up on the screen, so you can actually see here it is. Here's the JPEG of it, and here it is actually overlaid on the Earth. So very good overall. And what we need, if you remember from the repo here, is that we need the geotiff image, 18 bands, so 18 total, groups of 6, stacked in this order: blue, green, red, narrow, NIR, SWIR, and SWIR2. So when we open up the downloading portal here, you can see that there's band 11, 3, 10, FMASC, 04, SAA. It doesn't tell us specifically which one is which type, but fortunately enough, there is a guide here to tell us this. So this is just over at the USGS, and once again from Earth Data, so same type of thing. And what we want to look for is the HLS spectral bands, and you can see here that these are the codes that we're seeing in, you know, basically appended to all those images. So you can see here that for blue, it's band 2, green is band 3, red is band 4, and then these are edges, so you have to skip all the way down to 8A. B8A, which is NIR narrow, B11, which is the SWIR, and then B12, which is the SWIR2. So those are the bands that we need. So it's 02, 03, 04, 8A, 11, and 12. So if we go back here, you just need to track down those bands and download each of them. So for example, here's 11 in this image. I can go ahead and download that. You can actually also download these via AWS S3 if you want to kind of productionalize this and get access to some of this data that way. That's another way to do that. You could also do that with a stack catalog, and I've got some other videos on how to use those. But for just our purposes, we're just creating this one little image to go into the user interface to upload and go from there. So I've downloaded all these files, but basically you'll have to go through, download them, find 2, 3, 4. So here's 2, 3, 4, 8A, and then 11 and 12. So once you've downloaded all of those for the 3 dates that you want, if you're following along with this exact date structure, the 3 dates I pulled were 2024-09-20. If you see here in the file name, it's 2024, and then you have 264. So 264 is the date since the start of the year. So it's the 264th day of 2024. So I picked that image. I also picked an image in August. I believe that it is April 11th. So that is 224 here. So 2024, 224. And then the last one was in July. And let me just see which one that was. And that was July 12th. So it's 2024, 194. So yeah, just what you'll have to do, like I once again, is go through, download those bands 2, 3, 4, 8A, 11, and 12. So once you have done that, you can pause the video and come back to that once you've gotten all your files downloaded, and then we'll go into the next step. So once you've downloaded all your files, you want to pull them into QGIS. So these are all my files in my downloads folder. As you can see here, I'm just going to order them. So once you've downloaded all your files, go open them up in your computer in your folder system, and then basically just want to order them by name. You're going to want the oldest on top, so time 1, time 2, time 3. So that's going to be basically in reverse order. So we have 194, which is our July image, 224, which is our August image, and then 264, which is our September image. Work backwards on the dates. So what you can do is you can just drag all these files into QGIS, and you can load those up. And you'll see here it'll start loading in all the different layers, and these are all individual single bands. So our first step, like we said, is you need to merge those in that order, in that precise order. So what you want to do here is go to the raster menu, and then go to miscellaneous and go to merge, and then you can open up that menu. So we want to put our input layers in. We want to select all of them. But there is one tricky thing, is that the 8A is going to be out of order because it should go between up above the 11 here. So you just want to reorder that. You can drag and drop it. So for each one, that should be 3 times, put it above the 11, and the last time put it above the 11. So that will actually stack those bands in the correct order now. So first thing we want to do is just merge that. The one thing you need to select is that you need to place each input file into a separate band. Otherwise, we just mash everything into one pixel, which is what we don't want. We want 18 individual bands, which is what we're going to do here. You don't need to do anything in the advanced parameters, and then you can go ahead and click run to merge all of this. As you can see here, it just runs a GDAL command under the hood. It assembles it for you, and then it will just store it as a temporary TIFF here once it's created.
Hello.
Okay, so now we have that new merged band, and you can kind of see here as we merge in, it's just styling it randomly, but you can start to see where there's some of these different things that start to get merged here, and that you should be able to check out that you have in fact 18 bands. It's trying to render it as a multi color type, and you could change these and see some different things here happening behind the scenes and some cool colors, but you can start to see how a model could use this data to pick out what's happening here, because it can actually take a look and see, okay, well, you can start to see the shapes of the blues and the reds and things like that. And that's what it's using under the hood to kind of measure all of that. So yeah, I think it's pretty interesting overall to see all of that. So I think if we had all the images here, you can just play around with this just if you wanted to see what's there. And I think that's kind of the RGB. That's blue. Let's see here if I can get this right. And maybe 3, and then 1. Anyways, okay, so, but you can start to see as you can use these, how it's going to use the images under the hood. So this is the merged GeoTIFF, has 18 bands, has exactly what we need. The next thing we need to do is to clip that to a specific area. So we want to have something, an area that has, a small sample so it will run pretty quickly, in an area with a lot of fields. So what we can do here is, if we want to get that exact area we were looking at earlier, we can just add a quick OpenStreetMap base map here. I'm just going to quickly hide all the layers here, then turn this back on for the OSM standard layer. And then I should be able to see, I think this is Mankato here, and we were looking at somewhere just south of that here. Okay, so we found Mankato here. We'll just start to zoom in. I think we were looking at an area right down here. So somewhere around here where there were a lot of other areas. So let's just turn back on all the layers. And we can see here we have some different area with water, a variety of farms, things like that. So it should be able to pull some of these pieces out from the model. So let's go ahead and clip this. So we'll select that, we'll go into raster and then extraction and clip by extent. So what you have here is make sure you have that merged layer selected in this drop-down menu. The clipping extent, you just have to set the current map canvas. So you just click that button and that will set that for you. And that's pretty much it. It will just save it as a temporary file for now, which is fine. So we'll run that. You'll see here that this is the new one that's clipped. So if we, once again, hide all of our layers, turn this one on, it should be just in that area we specified, which is perfect. So then we can just hit export here. Save that, and then we'll just give that a name. I'm just going to save it to the desktop to be easy. Test TIFF, save, hit OK, and that will save that. So let's go back over to Hugging Face and the Prithvi example. And all we need to do now is just drop that file in. So as you see, I've done this a few times as I've been building this out. I'm going to head and drop that in. That will upload. And then to run it, we just have to hit submit. So the whole file is about 20 megabytes. This time here, I don't think is representative of actually how long it will take. It's taken less time at that scale. I've run some that are basically that whole image, and that's been taking forever. I think I started a new one when I started this demo here, and it looks like it's still running. So it's taking 5,800 seconds and still going. So hopefully it'll be done soon so I can see everything. But this one usually takes, maybe it took a couple minutes. I think this is an average of how long each run has taken. And it was much lower. And then when I started running it with bigger files, it went up. So I don't know if that's the case here. I also don't know what sort of compute infrastructure is running behind the scenes, because it does have some sort of process or something running this, and I don't know how powerful that is. So, it does take some time. So just be patient with it if you're waiting there. I'll pause the video here and then come back to it once that's completed so you can see the full thing that's complete. So I was finally able to get the model to predict. As you can see here, it's showing me 3 or 4 images. The first is our data from our time series 1, time series 2, time series 3, and then our actual predictions. So you can actually open this in a new tab, and you can see here that here are some of the different predictions. If we go and compare that with the legend, you can see the yellow is corn, our dark green is soybeans. So that seems to dominate a lot of this area here in the farmland. There's some pink, which indicates alfalfa. There are also some of these gray areas for like basically urban or built up areas, some of these sort of grayish green areas, which indicate wetlands. So we know that there's that river moving through here. And then there's these lakes or pockets of water, so we see that as well. And I believe it has a few winter wheat, an area for fallow or croplands, some other that's tagged in there as well. But that's mostly what it is. The pink and this pink shade here. Oh, then maybe that is natural vegetation. It's hard to tell which is which at this scale. But yeah, you can see this works overall. Graded the predictions, looks fairly similar to what we would expect. The big downside here is that I can't download this as a GeoTIFF. So it's not referenced or it's not geo-referenced. I can't bring it in. I can't do anything with it from here, which is really unfortunate. So what you would have to do is kind of go back in here. Once again, I think you can do some of this with Python. I would have to check that out. I didn't get that far into it. So just kind of printed the demo for today. But you can actually give it a shot, try this with Python, have the GeoTIFF. That would be a good next step if you wanted to continue a project like this. Now, of course, there's a scale problem here. Like just for example, I'm trying to run the unclipped image, which is this area we downloaded. And it's taking a very long time to do that. So I've been waiting around. Hopefully it will finish at some point, but we'll see. But the thing is, like, how do I do this if I want to do this over a massive area? area, maybe the size of a state, the size of a city, the size of even a country. What would you do? And we'll take a look at that in a future demo. I'll actually use Whereabouts to do that. They use the same type of foundational models, so you don't have to do any of the training or anything like that, but scale them out across a very, very large area using distributed computing. So we'll take a look at how to do that with the same type of workflow and use case there. So stay tuned. I'll have that video ready soon. If you have any questions on this or comments, feel free to use the comments. I'll get to those as best I can. And yeah, if there's anything else you'd like to see, feel free to drop those in the comments as well. I'm happy to kind of take these in different directions that are interesting to you. But hopefully this was helpful, gave you a little context on these foundational models using some of this data. And yeah, we'll see you next time.